right. Hello, everyone. Just so everyone's aware, a quick disclaimer. These presentations are designed to be 15 minutes in length, so please forgive us if we just completely skip over things or be very brief with some of these slides. So we're going to talk about performing semantic segmentation on an extremely small data set, and I'm Rodney.
I'm Hao.
So here's our problem statement, is how do we perform semantic segmentation on an extremely small data set of only 30 images, which are 1188 by 792 pixels, while achieving high generalization accuracy? You can go ahead. You got it. So real quick, semantic segmentation is the process of partitioning an image into the semantically meaningful parts and classifying those parts into one of a set of predetermined classes. So basically, another way to think about it is pixel-wise classification, since the ultimate goal is to classify every single pixel in an image to a specific class. Go ahead. So here's like a pictorial representation of what we're trying to do. Here is an original image taken of Regent's Hall, and here is what we call the ground truth image that we're hoping that we can generate something similar to this. This one was done by hand, by a machine learning algorithm. So we looked at two approaches to solving this problem. The approach on the left I'm going to talk about is we took our very large images and we split them up into a series of around up to 300,000 sub-images and trained a neural network to recognize those sub-images. And you guys can talk about the other approach.
Yeah, for the second method, we are still using the machine learning method.
Farther away.
Okay.
Right there.
Yeah. So the second method is still the machine learning method, but the difference is that the first method focuses more on the local information about the image, so it treats the image into small little bit of bits. But the second approach takes the image and the local structure as a whole, so that we would produce a more accurate result.
Yep. So the first approach, we're going to skip over this because we don't have time, but basically we talk about how we created the data. You can go ahead and hit next. Yeah, this is, we created a convolutional neural network using Caffe. And a quick note here, so we're trying to recognize 5 different possible classes from these images of Regent's Hall, namely the ceiling, the brick walls, the plaster walls, the floor, and everything else just gets thrown into this category miscellaneous. You can go ahead, yeah. So here's the results we got. We got around 61% accuracy, 56, 75, 52, and 75 on each respective class that I just described, and with a final accuracy for the object recognition of these little tiny sub-images, how good we were at classifying these little sub-images, of 68%. And now after we have all these sub-images, yep, you're good. After we have all these sub-images, we can then recombine them into one large image that'll look hopefully similar to that ground truth I showed you at the beginning. We can skip this. We just had really bad data. This talks about how bad our data is. So, yep. So here, Scott was just going to go ahead and flip through these somewhat quickly, but you can see our accuracies in the top right for object recognition, and then for the actual pixel by pixel of how close they were to being either right or wrong. And you can see even the best in the world neural networks for classifying semantic segmentation is only around 77% accuracy. So for us to be, in the upper 60s, lower 70s is very good, I guess. Here you go.
The second approach uses a similar technique, which is called the convolutional neural network. And the database we are using is we squeezing the original image into 20 by 20 images. And we use a single convolutional layer. It's a special kind of matrix that we will use to process data into another matrix that we will evaluate over. Right, we are using a single convolutional layer to process our data images and do a so-called batch normalization technique to make our results finer. Right. Okay. So our conclusion from this research is the larger our image is resized to, the better result we can get. And the batch normalization technique can greatly help our convergence of the neural network. It's basically a function, but we want a more precise function. So a batch normalization can give us a more precise function to use. And there's another layer called the ReLU layer. This gives you the non-linearity property when doing the segmentation, and that would help our segmentation as well. Yeah.
And finally, there are some demos, small demos here. So on the left-hand side is the result producing without using the ReLU, which is the nonlinearity commutative property. And the right-hand side, you can see with using that, it picks up more like details there. So, and this is showing the differences between the resizing image size. So before we have 20 by 20, and now it's resizing to the 100 by 100. And this is 500 by 500, so you can see the details. And the colors, which shows that different classes are more clear, and the details you can see more clear here. So that's how our project in the interim. Thank you.